Yeah, so it's my great pleasure to introduce and welcome Professor Catherine Gorle and her PhD student Nick. Catherine is an associate professor at civil and environmental engineering at Stanford, and she's also a member of Institute for Computational and Mathematical Engineering at Stanford. Before joining Stanford, Catherine was as an assistant professor at Columbia. As far as I know, Catherine is widely known for her pioneering research on multi-scale and multi-fidelity building simulation that incorporate uncertain quantification, reduced order modeling, and data assimilation. I think the way I understand it, ultimately her lab is interested in developing tools and models that can effectively support sustainable urban and building design. Primarily using computational fluid dynamic tool simulation and field measurements. So before I hand it over to Catherine, as she said, she wants to provide a bigger picture of what her lab does. I just wanted to say a few words. I wanted to acknowledge the support of our research initiative inside Autodesk. As you all know, we have an initiative called Net Zero Building. So I especially want to thank David Benjamin and John Locke and also Alex Tessier, who have all been supportive of my own collaboration and connection with this amazing research group. I should also mention that this collaboration has been enabled and really accelerated by a gift from our CEO, Andrew, to Catherine's lab, which came after I proposed and submitted this collaboration and funding request to the CEO office. So I also wanted to thank Angie Foss and Andrew Spermuli, who helped me during earlier stages to secure this funding. Yeah, so without further ado, I'll hand it over to Catherine to talk to you about the exciting research they've been conducting on simulating the urban canopy's impact on natural cooling. So Catherine, here you go.
Okay, thank you, Assam. Yeah, thank you for the kind introduction. And for the opportunity to present here today, and of course also for the collaboration, because this has been a lot of fun and very interesting for us as well. So I'm just gonna take like 10 minutes or so to walk you through like a broader overview of the lab and the work that we do, and then I'll hand it over to Nick, who has been doing the research on this specific project. So before I start, I always want to acknowledge all of the amazing people that I've been able to work with. So you see here, former students, current students, and then top left corner here is Nick, who will be presenting to you later. And we're a pretty collaborative lab. So yeah, what you'll see is really because of all the people that have been here. Our goal is really to focus on sustainable cities, because we know that the urban population is increasing very quickly, and that there is an urgent need to design more sustainable and resilient buildings in urban areas. And when you look at pictures of cities, right, you can imagine that the sustainability problems can be very variable depending on the location and the layout of a city. Can be pollutant dispersion, urban heat island effects, like general population health concerns, etc. But with my background in wind, we tend to focus on problems that relate to wind. And if you kind of take a more general view of that, there are quite a few problems where wind can affect sustainability. So on one hand here, we have pedestrian wind comfort and sometimes even wind danger, right? Making sure that at pedestrian level, the wind conditions are comfortable and safe. We have pollutant dispersion. How do pollutants from traffic or industry disperse in urban area? Sometimes that's related to natural ventilation and cooling, right? Because you can bring in outdoor air to ventilate and cool buildings, but then you want that air to be of sufficiently high quality as well. Ventilation and cooling can improve health and well-being of occupants and can significantly reduce energy consumption as well. Wind loading is a very important topic. There is billions of dollars of damages from extreme wind events every year. So trying to make our communities more resilient to these extreme wind events is very important. We've worked on all of these. There are two topics here that we haven't really worked on, but that I would be interested in exploring at some point. It's urban wind resource assessment and then urban heat island mitigation as well. And when you think about these problems, there are really two overarching challenges in all of them. First of all, there is inherent variability in the meteorological conditions that cover these flow problems. And then second of all, we are dealing with quite complex flow physics. These are high Reynolds number, very turbulent flow. Sometimes it's multi-physics as well when you think about pollutant dispersion or urban heat island mitigation, even for natural ventilation and cooling. At the same time, though, we're kind of at a unique point in time to address these challenges because we have more and more high-performance computing capabilities available to us. We have more and more sensing capabilities that allow us to actually measure in urban areas and get real-world data. And then we have more and more tools from uncertainty quantification, data assimilation, and machine learning that can help us bring the computations and the measurements together and really better predict and understand these problems. So the long-term goal of the research that we do in my lab is to get to efficient predictive modeling frameworks that can quantitatively support the sustainable building design and urban planning process. And we're primarily doing that using tools from uncertainty quantification, data simulation to achieve validation of models with field measurements to really represent the real world complexity out there. So to think about our problems, I like to put it in this kind of modeling framework where we have a model, right? But we know that that model has uncertainties. On one hand, you have that uncertainty because there's a lot of variability in weather conditions, which are usually the inflow conditions to our simulations. On the other hand, these models usually can't be first principles. We can usually not resolve all of the physics. So we have some uncertainty because we need to do reduced order modeling in there. And then when you can characterize these two uncertainties, you can propagate that through your simulation framework by running a larger number of simulations and get probability distributions for quantities of interest that you can then compare to field measurement. So in this process, this left-hand side is very important, right? Because if you don't characterize these uncertainties well, your output is not going to be accurate. So we think a lot about how to do that. And when you think about uncertainty in the inflow conditions, you then either go back to field measurements or you do weather forecasting simulations, so larger scale simulations. So in some sense, this is a multi-scale problem. And then on the bottom side here, the reduced order model outputs, you can characterize these uncertainties by doing high fidelity simulations or high fidelity lab experiments, usually on a problem that is slightly simpler, right, than the full scale application that we're looking at, but something that has the same physics and that can help us understand these uncertainties. And then the last step, if you have field measurements of your quantities of interest, you can couple back, right? You can do a comparison between the distributions you predicted, the distributions you measured, and then to do data assimilation to update what these uncertainties really are. So when we think about building these frameworks, we do usually tie it to an application because the uncertainties that might be most important or the models that might be most efficient can depend on the application. So we've done work on all of these four. When we started with pollutant dispersion and pedestrian wind, the model that we use here in the middle was a Reynolds average Navier-Stokes model. So it only solves for the mean flow and models all of the turbulence. So we had uncertainty because of the inflow conditions, and then we also have uncertainty because of turbulence modeling. And we propagated that through our simulations to get these probability distributions and compare. For wind loading, we're really interested in turbulence quantities. So the turbulence modeling was introducing too much uncertainty. So we ended up moving here to more expensive, but also more accurate large eddy simulations, and then just thinking about these uncertainties here. So we're not talking about that today, but if you're interested, you could always go to the lab website. There are a few keynote talks on there recorded that have information on this. So today we're going to focus on natural ventilation. And my last slide is to kind of show you what the big picture framework there looks like. So in natural ventilation and cooling, you have variability in the weather conditions, and it's wind speed, wind directions, temperatures, indoor, outdoor temperatures, building surface temperatures, etc. So you really have a high dimensional problem here, and using CFD to do that propagation becomes very computationally inefficient. So what we do here is we have our workhorse is a building thermal model or a building energy model. It could be something like Energy Plus, for example. And then we have weather data to characterize these uncertainties, and we can propagate that through the model to get our predictions with probability distributions. The challenge is that these thermal models use very simple models to come up with what the ventilation rate is and what the heat transfer coefficients are. And that can introduce a lot of uncertainty in these predictions. So the work that Nick will be showing you is really looking at high fidelity large eddy simulations and how these can help us come up with much more accurate models and correlations for ventilation rates and heat transfer coefficients. So with that, I'll stop sharing my screen and then I'll hand it over to Nick. And I'll also mute myself, Nick.
Sorry, pulling up the slide. All right, Catherine, does this look correct?
No, we see like your whole, I can show you my screen so you know what we see.
Okay. I think this is not going to work.
You can try using the swap button is what was recommended.
It's all right. I unplugged my other monitor, which was also a big TV. All right.
Yeah.
Great. Okay, so I'm just going to quickly reintroduce myself. My name's Nick. I'm a third-year PhD student in Catherine's lab, and I'm going to be getting into the details of simulating the urban canopy's impact on natural cooling. So the challenge with building cooling really is that there's kind of a paradox between the more we use building cooling and the more urban heat we are experiencing due to climate change. And to kind of give a sense of the scale of urban cooling, by 2050, it's expected that if current trends continue, building cooling alone will use as much energy as India and China did in 2018. So can natural cooling help with this problem? And when I talk about natural cooling, I really mean driving cold air through a building with two forces, and those are pressure-driven wind forces and buoyant forces. And the schematic's trying to get at both, and it's kind of showing that a wind field creates a positive pressure on one face of the building and the negative pressure on the other, and that is driving flow through this building. And we want to do this at a large scale, but the challenge really is that we don't have a good sense of how the urban canopy affects these ventilation rates. So each building is in its own little world where their surrounding buildings are creating a very unique flow field that it's experiencing. And we want to be able to have reduced order models, as Catherine discussed, that can kind of get at some of these effects that are pretty hard to predict. And for instance, the effects of the surrounding urban canopy is completely omitted in Energy Plus, and it's basically excluded in all reduced order models for natural ventilation and cooling. So if we want to think about natural cooling on a large scale, we really need to get better ways of predicting this effect. And what we can do well now is we can look at a wide array of weather data. We have access to pretty sophisticated building energy models, much more than the one I'm going to be talking about in this talk. But the kind of question remains, and I would say like the weak link in predicting natural cooling is the effect of wind, and specifically these really small local effects of wind around a building. And before I say natural cooling too many times, I just want to kind of demystify it for anyone and say that, most of us, I think we open our windows at night, we try to let cool air in, we close them during the heat of the day. And this is really kind of the idea behind natural cooling, is how can we do this the most efficiently to offset any sort of air conditioning use. And if there's one point I'd like to get at in this talk, and Catherine kind of started us down this road, is that these high fidelity simulations of wind in urban areas really can underpin better reduced order models for natural cooling. And I'm going to try to talk about how these simulations can kind of get to the important parameters that we need to capture to have effective reduced order models. But before I jump into the exact simulation of wind, I'm going to talk about kind of the general state of cooling across California, both looking at weather data and at building energy models. And then after discussing the wind simulation, we're going to go back and try to apply those results across California and see kind of what we can get. So California is divided into 16 climate zones by Title 24, which is our energy code. These climate zones are based on energy use, temperature, and weather. They're not like a traditional like desert or mountain area. But across climate zones, we want to have a standardized measure of cooling need. And really hot days require more cooling, and but if we have a lot of kind of medium hot days, that still requires a lot of cooling. So a way of combining these ideas is the cooling degree day, which kind of sums the amount of cooling over the number of days in a period of time. And how this works is you take the mean temperature described kind of naively as the average of the high and low temperatures during any day, and you see how much that exceeds a baseline. In this case, we're using 21 degrees Celsius. And then the final little bit of complexity is we want to focus on days with a significant amount of cooling, ones that aren't kind of right on the edge. So we're going to stipulate that the mean temperature for that day should be above 24 degrees Celsius. So if we look at cooling degree days across California, most of it is in kind of the thousands per year. These are concentrated largely in kind of the Central Valley and then especially in the inland part of Southern California. And they're really in the summer months, as we'd expect. But how often can these cooling degree days be addressed via natural cooling? So, if there's a really low temperature, if the nighttime temperature the subsequent day is very high, it's really infeasible to say that natural cooling is a solution, because no matter how much air we can drive through the building, we're never going to achieve this comfort temperature we're targeting. So this natural cooling degree day adds the condition that the subsequent low temperature should be below 24 degrees Celsius. So it's basically putting a condition on the nighttime low. And if we reapply this across California, it really is fairly similar. So what this is saying is that most of these cooling degree days in California theoretically could be addressed with natural cooling if that natural cooling was efficient enough. And the one exception is kind of climate zone 15, which still has the most natural cooling degree days of any climate zone, but there's just so much, there are so many cooling requirements, and the low temperature is not getting low enough in a lot of these days to support the cooling. So we're losing, hundreds of cooling degree days when we're thinking about natural cooling instead. But overall, it's very promising to see that most of the time natural cooling is a feasible solution, at least in California. And these natural cooling degree days, they only rely on the weather data, and they're a very kind of hopeful way of describing natural cooling, but they do also provide a good place to start if we're talking about building energy modeling. And Catherine kind of touched on these models earlier, but what I do is I run 600 weeks from a typical year and then run it across all 16 climate zones and look at how a simple building is kind of interacting with these outdoor temperatures. And this helps us answer two questions. The first is, do these natural cooling degree days, are they really representative of the cooling we see in a building energy model? And the second question is, what are the relevant wind speeds and what are the relevant indoor-outdoor temperature differences when we're trying to think about simulating wind in greater detail? So the reason a building energy model is important is there are all these physics that are really getting at what the natural cooling degree day is calling the mean temperature, the average of the high and low temperatures. That's supposed to be kind of standing in for the indoor temperature, but the indoor temperature is affected by, for one, solar radiation. So during the day, solar radiation is driving a lot of heat loads into this building, and then conversely, the soil at the bottom of the foundation is kind of acting as a constant temperature boundary condition during the day that is soaking up heat, and during the night that's putting off heat. And then the outdoor temperature is interacting with the indoors through a combination of convection, radiation, and conduction. There's just a lot of things going on here that aren't captured if we're just looking at kind of a cooling degree day. And I'm not even including in cooling or heating loads. So I'm apply this kind of modeling framework with the physics described in the last slide to a simple house. It's 6 meters high. There are 5 rooms. It's a fairly small house, but 6 rooms is the median number in California. And the rooms are 4 by 4 meters, and the ceiling height is 3 meters. And across California, almost 100% of single-family homes are wood frame construction, but they do have a large range of insulation values. And this goes from what I'm describing as heavy insulation, which have these higher values of resistance. And this is kind of in line with the most up-to-date California energy codes, all the way down to this light insulation case, which is kind of representative of like early 1990s energy codes, or just areas that don't have very many very high, very strict regulations on insulation. And as Catherine also mentioned, there's a large degree of uncertainty in some of the coefficients that we care about for these building energy models, specifically convective coefficients and radiative coefficients. So we sample from a range of these coefficients when we're running the building energy model to try to account for this uncertainty. And once we start thinking about cooling in the framework of an energy model, we want to think in more detail about what natural cooling means and when it's going to start. So the first 2 conditions here, we want the nighttime low to be below 24 degrees Celsius and the indoor temperature to be above 24 degrees Celsius. This is kind of the baseline conditions that we've laid out in the natural cooling degree day. But then we also want to pinpoint a time when cooling starts, because if we care about things like the indoor-outdoor temperature difference, that is really varying throughout the day. So it's important to know when occupants might want to open their windows. So the first condition we have is when the indoor and outdoor temperature equalize. So this is kind of the first time that natural cooling is viable, and we think occupants are likely to open their windows. And the second condition is at 11 p.m. So this is kind of what we think is the latest time people are likely to open their windows. And this also comes out of ASHRAE's design guide for night flushes. So it's a bit of a guesswork, but also it does come from ASHRAE to a certain degree. And the building energy model shows that in both of these conditions, so the indoor and outdoor temperature being equal and this 11 p.m., the pattern of degree days by which the indoor temperature exceeds 24 degrees Celsius at the time of initializing cooling follows the natural cooling degree days pretty closely. So this is a good indication that, natural cooling degree days are an effective kind of pattern, but they don't really capture like a sense of the absolute value of the number of days exactly. So we're seeing that using the building energy model, it's kind of reporting a more exact metric for a degree day that is a bit different, but largely follows the same pattern. And it largely is fairly similar across the 2 ventilation times. So it seems that exactly when cooling is initiated is not hugely important. And now if we kind of switch gears a little bit to think about the simulation, we can also pull out this indoor-outdoor temperature difference. So in the first cooling scenario I described, which is when the indoor and outdoor temperature differences are 0, it's by construction, the indoor-outdoor temperature difference is 0. But in the second cooling scenario at 11 p.m., this indoor-outdoor temperature we find on average is 5 degrees Celsius with about a 2 degrees Celsius standard deviation. And now if we're thinking about the simulation of wind, we want to know kind of what are the average wind speeds at the time where we're initializing cooling. And interestingly, across California, the higher wind speeds at these cooling times kind of match with these higher degree days. So this is a really good promising indication that wind-driven natural cooling seems like it can be effective with this kind of matchup of climate zones that require cooling and have higher wind speeds. And during and if we look more closely into these wind speeds, on this first cooling event, it's around 4 meters per second, and in the second cooling event at 11 p.m., it's closer to 2 meters per second, kind of like 2.75. But for elegance, we'll say that the two wind speeds of consideration for the LES simulation are going to be 4 meters per second and 2 meters per second. So I showed this house earlier, and now I'm going to talk about it in the context of the large eddy simulation and the CFD. So the interesting thing about this house is it really functions as a probe of 4 different ventilation types. So on the bottom left is this corner ventilated room where 2 adjoining walls have openings. In the bottom center, we have a single-sided room where there's only 1 window. Then on the right, there's a cross-ventilated room where these 2 windows on opposite sides, which is kind of the most simple version of natural ventilation and cooling. And on the top left is this dual room ventilation where there are 2 rooms with 3 windows total combined, joining with an open door. And these different ventilation types aren't interacting with each other. They're in isolation within the single house. And this really allows us to get into kind of how they work with respect to one another. So in the simulation domain for the CFD, we have 4 quadrants, each with the same group of 35 houses. And in these groups of 35 houses, there are 5 houses where we're explicitly simulating the flow of the fluid through all of these rooms. And we also, by creating these 4 quadrants with rotational symmetry at 0, 90, 180, and 270 degrees, we're able to offset the effects of kind of infinitely repeating the same straight urban canyon, which we found can be problematic and isn't very representative of real urban areas. And we also are able to capture 4 wind speeds per simulation. And now just to stand back, it is an idealized geometry that we're simulating, but it does match with, here's a picture from, I believe this is from Sacramento. And, you know, there is kind of there are areas that look like these idealized straight street regions. So I already talked a little bit about the wind speed and the thermal and the temperature difference for the large eddy simulation, but there are some other important parameters. The first is, and I know the talk is titled The Effect of the Urban Canopy on Natural Cooling. So how dense is the urban canopy? So we have on the right this high density case, and on the left this lower density case, which is about 50% more spread out. We also care about the wind angle. So we're going to look at wind angles from 0.45 onwards, so 8 wind angles total. There are 5 house locations. So these houses are, you know, they're the same in every way except where they're placed in each quadrant. So we want to look at the effect, basically, that the discontinuities and the different quadrants have on houses that are far away, that are otherwise have kind of the same surroundings. And lastly, we have these 2 parameters I'm pulling out of the building energy model. The first are the wind speeds, 2 meters per second, 4 meters per second, and the final one are the temperature differences, 0 and 5 degrees Celsius. So I'm going to step back a bit and give some context on LES simulation. So on the right is the flow field through one of the rooms during this kind of natural ventilation. And what the LES does is it filters the Navier-Stokes equations, so small turbulence scales are modeled and larger turbulence scales are simulated directly. These types of simulations are less studied, and they're not the industry standard, which is generally using more turbulence modeling. But importantly, these large eddy simulations help us capture transients. So if you look at the airflow through these rooms, there's a lot of kind of transient events. And specifically for the single-sided case, the only ventilation there is coming from transient flow in and out of the window. So while these simulations are more complicated and they do require more expertise, they also have the potential to be more accurate. And in our specific LES, we are using the Charles solver, which is developed by Cascade and part of Cadence. And we have periodic boundary conditions on all sides and a slip condition at the top. And what we're trying to achieve is kind of a neutral atmospheric boundary layer in the simulation. So now I'm going to talk more about defining the ventilation rate. So here I'm showing a tracer initialized in the house as the airflow comes and kind of brings that tracer out into the larger domain. So we describe this instantaneous ventilation rate in the most generous way possible, which is taking the absolute value of all airflow through a window. So for like the single-sided ventilation case, if we didn't have this absolute value, this integral would integrate to 0 because it's incompressible. So this ventilation rate captures both the mean flow and the transient fluctuations at all windows. And then specifically, I'm going to be looking at the time average ventilation rate across the simulation, which I'm just calling Q. Now, going back to the house, the first thing I can do is I can say, okay, how do these different ventilation types compare? So the highest ventilated room is this dual room ventilation, followed by the cross ventilated room, and then the corner ventilated room. And finally, the single-sided ventilated room is kind of an order of magnitude less. But interestingly, these red bars are showing the range of results as I go through all of those parameters I discussed earlier. So the urban density, the wind angle, the house location, the wind speed, and the temperature differences. So the range of results is almost greater than the average ventilation rate. So this is kind of indicating that we want to have a reduced order model that can do better than just predicting kind of the average across all parameterizations. So the first kind of step to look at is what happens if I average across urban density. So these green range bars are showing the average results for the low and high urban density cases, and it does reduce the spread a little bit, but there's still a high degree of variation. So next, I can average across wind angle. So now these range bars are showing kind of the range of results if I take the average across all wind angles. So once I'm averaging across wind angle, I'm really getting a smaller range. And I would say this is kind of the first time where you'd say, well, this prediction seems kind of useful because the range isn't that large once I take away the effective wind angle. And lastly, if I take away the effective house location, these purple bars are just showing the effective wind speed and of temperature difference, and it really is quite small. So this is kind of giving a sense of what is important. And now I'm going to delve a little bit more into these different parameters. So first, I can split the results by density. So whereas before I averaged across urban density, now I'm splitting across the urban density. And interestingly, in the low density case, we're seeing much higher ventilation rates across all rooms than the single-sided room. Now, focusing in on the corner room, once again, the low density case shows much higher average ventilation, and it also shows a much higher range of results. And I forgot to mention, but I'm reporting the ventilation normalized by the wind speed. So otherwise the wind speed would have a very large effect. Sorry for that. And now, so the range of results across the low density case really is much higher. So there's something about having a low density urban area that makes it more sensitive to wind angle, is basically what this plot is showing. So why is this? And so now I'm going to look at 4 different mean wind fields at 1.5 meter height above the ground. So this is at window height. So the top row is showing this 0 degree wind speed where the wind is aligned with the urban canyons, and the bottom row is showing it diagonal to the urban canyons. So the right side are these lower density cases. And what's happening in lower density cases seems to be that they're supporting kind of greater variation in wind speed, whereas the high density cases, they kind of want to snap the wind speed along the direction of the primary urban canyon. So it seems that even when we kind of change the wind direction in the high density urban area, that's not changing so much what any individual house is feeling. It's feeling the wind more along the urban canyons, whereas the low density regions, these houses are feeling wind angles that are more variable. So if we look specifically at I'm saying that the low density case is more sensitive to wind angle. So let's look at the corner room, the effective wind angle in the low density case. So the first thing is that the best ventilated direction is this 315 degree angle. And that is aligning with kind of cross ventilation, so to speak, of this corner room where you can draw a line between the two windows. The next case is this 90-degree case where there is kind of direct airflow into this window, and there's no house immediately upstream of the building. So this is allowing a pretty kind of direct path for flow through that room. But the other thing is that, sorry, this is a bit of a jarring transition, but when we look at wind angle, the effect of house location also becomes important. So here I'm showing this blue, red, yellow, green, and purple house in all these wind angles in these like sub bars in each petal of this wind rose. So let's specifically focus in on the 0-degree case. So in the 0-degree case, the center room actually of this urban area has the lowest ventilation rate. And that is kind of, I would say, counterintuitive, because you'd think this urban area, this quadrant is aligned with the wind. You'd think it would kind of support the highest wind speed in the center of the quadrant. But that's not really what we see. Instead, the upstream buildings create this wake effect that is causing a momentum deficit around this in the center of this area and reducing the ventilation rate in that building. Now, interestingly, the highest ventilated cases are not on the edges of this urban area, but on the second and fourth rows. So now if I look at the root mean square of the velocity variations, this is kind of a proxy for the turbulence. We have higher turbulence at the second and fourth row, and we have much lower turbulence at the edges of this domain. So it seems like the best ventilated rooms are the ones that are experiencing relatively low momentum loss from these upstream buildings while taking advantage of the turbulence they're created. So as I said earlier, our measure of ventilation is accounting for both these fluctuations and this mean ventilation. So there seems to be kind of a happy medium based on where houses are located in the larger urban canopy that's creating better ventilation. And now what I'm left with here are, in these purple bars, are variations due to wind speed and temperature difference. So these are all the parameters I pulled out of the building energy model. And at least in this one case, the range of results is fairly small compared to the range even relative to the placement of the house. So if I go back to the results from this simulation, we can kind of get at a hierarchy of possible reduced order models. So what we're seeing is that what the first reduced order model should do is we want to capture the effect of urban density and wind angle. And these are kind of tied together because the wind angle is related to how a house is experiencing the surrounding buildings. And this takes care of these kind of red and green range bars. So if we can get those down more towards this blue range bar, then our uncertainty in our predictions is fairly low. And this is kind of becoming a useful model for ventilation. Then the next kind of ventilation model would then maybe look more at these surrounding wind field and the effects of buildings that are more farther away from a house. And then lastly are these wind speed and buoyant effects, which in this case, we're finding to be very small compared to the role of the urban canopy and the wind angle. So I'm going to step back to talking more about cooling and finish off by talking about ventilation across California. So something I've extracted from all of these LES simulations is this kind of ventilation rows. So here's the corner room, and here I'm showing the ventilation rows for that. So this is for all of these wind directions, I'm showing the degree of ventilation we're expecting. And there is still a pretty high degree of uncertainty because I'm averaging across urban densities, and that's what these red bars are showing. But I can go and look at the wind roses in all of these climate zones across California and match it up with these ventilation roses and get these optimal alignments of the rooms. So on the right of this slide, I'm showing the different angles of which these rooms should be rotated to get the most ventilation. And the negative angles are a proxy for first mirroring the room and then rotating it. So these optimal alignments have an associated yearly cooling. And I'm going to call this a ventilation degree day. So this is a product of the ventilation rate and the number of days and the number of degree days of cooling in a year. And if I compare these ventilation degree days, they're pretty similar to both the degree days from the building energy model and to the wind speed I'm pulling out of the weather data. And that isn't that surprising because both of these quantities are kind of the primary things that are impacting the ventilation degree day. But to look at one kind of example of interest, if I look at the wind speed between climate zones 13 and 14, climate zone 14 has the highest wind speed of all the climate zones, significantly higher than 13. But 13 has a higher cooling load as predicted by the building energy model. And then if I translate this to the ventilation degree day, I'm seeing that climate zone 13 and 14 actually have pretty similar predicted ventilation degree days. So we are able to add a bit more detail on how effective wind-driven natural cooling is compared to the building energy model or just the weather data. So I can look at the ventilation degree days across now all of the rooms, and they are mostly following the same pattern. And this is just because the degree days predicted by the building energy model are consistent across all climate zones, and the corner, cross, and dual ventilated rooms ventilate fairly similarly. But something interesting is that while the dual ventilation setup was the most effective in the large entity simulation, once I compare it to the wind roses at the time of ventilation, the cross-ventilated room actually becomes the most effective form of ventilation. So what this is saying is that the way the wind angles at which the cross-ventilated room ventilates well align more closely with the standard wind roses we're seeing across California at the time of ventilation. But even though most of these ventilation degree days are pretty similar for all the rooms, they are relying on different alignments of buildings. So the corner and cross-ventilated rooms are actually aligned pretty similarly in all of these optimums, but the dual room and the single-sided ventilation are using kind of different alignments. So to create all of these to achieve all of these kind of peak ventilations at once would require kind of some sort of theoretical optimizing of the layout of a house. So on the left here, I'm showing the average ventilation based on this kind of optimal house layout. And then on the right, I'm showing the ventilation I'm achieving with the layout I've used throughout the large eddy simulation. And actually, they're not that different. So it seems like the exact way that the building layout is constructed isn't hugely important as long as it's aligned well with the dominant wind directions at the time of ventilation. I mean, I think this is because the cross-ventilated room and the corner ventilated room are both able to create pretty large ventilation rates when they're aligned together in the layout I've set up. So I've started the talk by discussing kind of large-scale assessments of cooling, and I've done something that looks kind of like a large-scale assessment of natural cooling. So how complete is this? Well, once again, I'm showing the ventilation rows for the corner degree room. There's still a lot of uncertainty based on the effective urban density. And really the only thing I think we've pinned down is the effective wind angle here. So to get a more complete assessment of natural cooling, we would really need to go in and pick out kind of the exact urban densities and adjacencies, or at least make some sort of qualitative assessment of urban densities across California. So I think this is a really interesting area that could use more study. We also aren't really accounting for any sort of surrounding flow field effects or detailed effects of the exact wind speed and buoyancy here. But this just goes to show that even using simulating wind in the urban area, using this very detailed simulation that is beyond what industry standard is, we're only kind of getting a little close to our ideal predictive capability for ventilation at a large scale. And we really need to both kind of make progress on that front to develop these more complete reduced order models, and to develop better ways at quantifying or at least qualifying urban areas at a large scale to kind of put those into the model and understand like what is the urban density in like Sacramento compared to the Bay Area or compared to, you know, Los Angeles. So with that said, I hope I kind of was able to shed light on applying these more detailed simulations towards developing a reduced order model and show how that can be applied at a large scale. And here's a little bit of direct numerical existence of wind that I took on my phone. So thank you.
Thank you so much. We can open up for questions now if anyone would like to come off mute and ask our speakers questions. I actually had one to start us off. I was wondering how like urban features such as fences and landscaping could affect your current simulation.
Yeah, that's a great question. I think they can have a pretty significant effect. Some features more than others. One of the things about features like landscaping or trees is that we can treat those generally as a more constant effect on the wind field. So if we were to include those, it would be a bit simpler than these kind of very strong features like the houses and the urban layout. But that said, things like fences, I think they would play a pretty large role, and that's, I think, definitely an area of study.
I think Alex, I think you had your hands up first, and then we'll go to Maren.
Sure. Great presentation. I really like the top-down analysis and how everything goes together. Yeah, the flow field details in the individual rooms are really particularly interesting. But the question I had was, I know it's not covered by the study, but in years past, when we used to do similar work, we were always nailed on the effects of evapotranspiration of vegetation and how much that can change the delta T in a surrounding area. How much of an effect do you think that would have on your findings? It's something that's very difficult to normalize against because it's dependent on vegetation and solar gain and the kind of vegetation. So there's parts of California, like you said, that are very desert-like, and they're going to have very different foliage. How would that affect your overall analysis of the different regions of California?
Yeah, that's a great question. Let me start by saying that is not my area of expertise. However, for what it's worth, I think that is something that is very impactful for the urban heat island effect, is my understanding. And this is something that I think is much more studied than the effect of urban wind. So, and I know there are groups, in the same building I'm in studying the effect of evapotranspiration, and especially from vegetation. So it seems like it's a very hard problem, but I think that is one way that really getting a full understanding of natural cooling would probably include that type of thing. Hopefully we could borrow that from more of this work into the urban heat island effect and kind of plug the flow field into to kind of round out the picture of wind-driven natural cooling.
Yeah, if I could jump in quickly, I can go sit next to you next.
Okay.
Yes, welcome. I think these are things as well that you could like using data, right? Because there's lots of temperature measurements available today in urban areas, and like even the purple air sensors give us very localized data of what indoor-outdoor temperatures are. And these temperatures are an input to the eventual building thermal model, right? So just using measurements, like we don't necessarily need to change our model for that. The LES simulation doesn't have to be rerun. Yeah.
Thank you.
Maren, did you want to go with it?
Yes, thank you very much for the very informative presentation. I have some basic questions. So the question that I have is that, are you able to do similar type of studies using simpler 1D models or energy plus models instead of the using LES. And if you were to use energy plus models for these type of studies, would your findings be any different? Yeah, so it's mostly about that. And I have a follow-up question after you answer.
Okay. So first I'll talk about the energy plus models. So the energy plus model is more sophisticated than the building energy model we've used. I think it would give us fairly similar results for the building energy modeling. The challenge with energy plus is it has a very rudimentary treatment of ventilation, both looking at the effect of the surrounding wind field. So I touched on that earlier, but energy plus doesn't include anything about the effect of surrounding buildings. The other thing is that Energy Plus uses a network model for flow in the room that is kind of I think built for more like duct flow. It's not really meant for natural cooling exactly. So it's
so you're not able to do the same studies using Energy Plus models.
You could if you could implement a custom ventilation reduced order model, then I think that would be a great place to start. But by default, it's not that amazing. And then if we look at like the industry standard for these more complicated simulations, which is RANS modeling, which is modeling all the turbulent scales, that doesn't include these transient fluctuations. So you can't get anything about single-sided ventilation. And it also does a pretty poor job of capturing building wakes. So neither Catherine nor I think are that thrilled about running giant LES simulations all the time. It's very expensive, but what other people in the lab have found is that it's really kind of the basic need is these larger LES simulations.
The ultimate goal is really that you run the smallest possible number of these LES simulations to come up with much better ventilation models that you can implement in something like Energy Plus, right? So a ventilation model that is actually going to think about what is the orientation of your building with respect to the wind direction, what is the density of the surrounding urban canopy, eventually maybe what is the density of vegetation, right? So that you have a few more design parameters that you can put into that model that will reflect that complexity much better. I think to get to these models, we need to run the LES simulations, and we need to do that in a smart way, right? So we don't run millions of them, but we can run a few hundred and come up with a good model.
Yep, very cool. Yeah, you answered my second question as well. So
okay, nice.
All right, do we have any other questions? All right, I think that's a wrap. I want to thank you guys for presenting your really interesting work with Autodesk Research today. Thank you, Hassam, for making the connection, and thank you everyone for joining the call. And if you have any other speakers that you would like to recommend for our series, please feel free to message me. Awesome. Thank you, everyone. Have a great rest of your day.
Thank you, and thanks for the great questions.
Bye.
You.